All right, hello, my friends. Welcome back to this is Historical Geology 1404. This is the last lecture of the term. Now, I say that, but I need to be very clear, especially for my high school students. You are still required to be here for every class session until the end of the term. So this is our last lecture. On Thursday, we will have our final exam review, and your final exam will open. I was hoping that the following week we would be okay, but I received instructions yesterday that even though the term ends on the 9th, and you and I and our class here will be done on Thursday this week, all high school students are still required to be here for the full class period on Tuesday, the 9th next week. I was told that yesterday. So we'll just hang out, I guess. And you can, we'll play poker. We'll do something. You guys can finish any last-minute assignments if you like, anything like that. Take another crack at one of the labs, whatever you want. I was really hoping that this wouldn't be the case. So today is your last lecture. 2 days from now, Thursday, is our final exam review. So please come prepared with questions. And online students, please, send your questions before then. So we can have a good review session. And then next week, a week from today, the 9th, the last day of the term, we are still required to be here, at least my high school students are, which applies to everyone except Autumn. So you don't have to be here next Tuesday. You could if you want. You can just hang out with us. But yeah, all my high school students, you will need to be here with me next Tuesday for the full class session. Or next Tuesday, I should say. Yeah, Ryan.
This is the last lecture?
This is our last lecture. This is the last new content you're getting.
I thought we had 2 more lectures.
No. So y'all weren't here last week on Tuesday, but because the ECISD was on break, but the college was not. So I still lectured. I recorded that and posted it on my YouTube channel for you guys, like I said I was going to. Okay, so you have content on my YouTube channel that is available for you from the lecture I did last Tuesday. Okay, so you'll definitely want to watch that and catch up and take your notes. I was hoping maybe you would have done that before the lecture today, but if that's not the case, that's all right. You'll just need to go back and catch up on that before the final exam review on Thursday, okay? What's the what? Oh, for anyone that doesn't know where my YouTube channel is, it's Heart Rock Geology, and I think I have posted some links there. That's where all of the videos for the labs and stuff are as well. Yeah?
So what were the lectures that you missed? Huh?
You missed the Permian, the Carboniferous and Permian, and then the Mesozoic. So we talked about the development of reptiles, and then we talked about dinosaurs and mammals diverging from there. And we talked about the age of dinosaurs, the Mesozoic, the Triassic, Jurassic, and Cretaceous. So all of that is in that recording, which is on my YouTube channel. And then what we're talking about today is the last lecture, which is going to be the Cenozoic, the time period we're in right now. Okay? And we're going to end with modern history today. I'm going to go ahead and get started on that. There's an online meeting that I am supposed to start listening to at 11. So I'm going to get started on our lecture so that we can jump into lab time and I can listen to that.
Good morning.
Yes? They're not here today? They are. All right. Well, they'll get here when they get here, I guess. I graded something that was not due yet. Yeah, I know. So when are you saying that because I put a 0 on it? Yeah. So what that does is this is something that I do, and you were in 1403 with me, so this is the same thing that I did there. Last week of the term, I throw 0s on anything that hasn't been turned in to kind of let you know, hey, this is a consequence if you don't do the work. Because there's a lot of things that have not been turned in yet, which were due weeks ago. And I put 0s on those too. I basically just blanket 0 to everything that has not been turned in yet so that you guys can feel the pressure. Because coming fresh off a break with another break on the horizon next week, it's going to be really tempting to let things slide. Don't do that. Don't do that, my friends. The last thing you want to do is work hard for 7 weeks and then trip right at the finish line and fail. Please don't let that happen. I hate seeing that, because I know how hard you work, and it would suck for me to see you trip right there at the end. All right? So anything that has a 0 on it can still be completed. Please do that. All right? You have a week left. Okay, that being said, everything needs to be turned in by the evening of the 9th, because on the 10th is when I start calculating final grades. I hate it when they do this. I hate when they make the final day of the term on a Tuesday. It's usually on a Thursday, because then I can say everything's due Thursday, I'll come in Friday and grade everything and finish off the week like that. But for some reason, it's ending on a Tuesday this term, which means that I come in on Wednesday to start doing final grades. Okay? All right. Any last questions before we jump in? No? Okay. So, when you go back and you watch that lecture posted on the YouTube channel, you're going to see that at the end we finish with the Cretaceous extinction. That's the extinction that killed the dinosaurs. Okay? It didn't only kill the dinosaurs, it killed all our flying reptiles. It killed all our swimming reptiles, which both groups are often misconstrued as dinosaurs. There were no swimming dinosaurs and there were no flying dinosaurs. Those two groups were separate from dinosaurs. Think of them as cousins to dinosaurs, but not true dinosaurs themselves, okay? We also lost the ammonoids that have stuck around for so long. We've had the ammonoids in the ocean for a very long time. The ones that are curled up on themselves. There it is. These guys, right? We lost them. They died with the dinosaurs. End Cretaceous extinction. Rudis, which you'll hear about in that video as well, if you haven't watched it yet. These were a very prominent bivalve group that existed really only during the Cretaceous. They're an index fossil for the Cretaceous. They made massive reef colonies and were very important for the underwater ecosystems. But they died off with the dinosaurs as well. Okay, so this isn't the largest extinction, but it was a pretty big one. Definitely a mass extinction. Emails. Okay, definitely a mass extinction. And what happens after an extinction? What's the pattern we've seen so far? What follows an extinction? New life. And what do we call this? The development of new life, the spreading of new life through all these niches. We call that? And irradiation, yes, adaptive radiation. Okay, so after an extinction, there's always a radiation of life, which means that it kind of blasts outward, it explodes outward, it diversifies extremely quickly and fills in all the available spaces. Okay, would you mind closing the door for me while you're over there? Thank you. Okay, so what fills all of these niches? Well, what's gone? The dinosaurs filled a very large ecological niche on the terrestrial surfaces, on the continents. Flying reptiles filled a lot of ecological niches in the air. The swimming reptiles were the main super predators of the ocean. The rudis were main reef builders. The ammonoids were a major part of the food chain in the ocean. So very large, important niches are left vacant. What fills these things? Well, on land, we see mammals. In the oceans, different types of bivalves. The ones we're more familiar with today, oysters, clams, scallops, etc. In the air, what do you suppose starts filling the ecological niches in the air? Birds. Right, this is where, even though we've had birds since the Jurassic, the fossil record seems to indicate, this is where birds really take off. Thank you. Okay, there it is. Okay, so lots of birds start to fill the skies here, okay? And then we see reefs actually being formed by the corals that we have today. During the time of the dinosaurs, most reef systems were formed by what are called hexacorals. Well, hexacorals survive but change into what we call scleractinian corals, which you will have seen in one of your labs. Okay, scleractinian corals are the type that form our reefs today. So after the dinosaurs go extinct, we see the development of all these niches being filled with the sort of things that you and I would look around and see and recognize today. This is about 66 million years ago is when this extinction happened. Okay? So 66 million years ago to 23 million years ago, this is what we call the Paleogene, Neogene, Quaternary. But this 23 million years, we're starting off talking about the Paleogene right now in this slide deck. Okay? So this is what a mid-Paleogene sort of ecosystem would have looked like. It looks very familiar to us. We see pine trees, we see flowering plants, grass, right? Bushes. And these animals, while we may not recognize the animal specifically, this one kind of looks like a rhino. This one kind of looks like a horse. This one kind of looks like a lion. This one kind of looks like a horse. You recognize it. It's familiar. It's not exact, but it is familiar. Okay? All right. So, talked about all of that, pretty much just summarized all of that. All right, so all of the incredibly diverse forms of life in the ocean, remember the ocean is where life began, lived for the longest and spread from there onto land. So evolution and the history of life in the ocean is far richer than that on land has been. Okay? All our foraminiferans are microscopic little organisms that live and die and fall into the sediment at the bottom of the ocean and get turned into oil and things like that later on. We go from having tens of thousands of species in the ocean during the time of the dinosaurs. You're basically drinking soup if you were to take a mouthful of seawater. Only 3 species that we can find fossils of survived this extinction. Those microorganisms, those fossils, those foraminiferans came this close to just being gone. Only 3 species out of thousands and thousands survived. And from there, we have the vastly diverse group of foraminiferans that we have in the ocean today, but they only came from these 3. Now remember, that's only 3 we can find. There may have been 10, 12, 400 species that survived, but we only have fossils for 3 of them. That's how incomplete the fossil record may be, and we don't even know it. But for now, we can only work with the data we have. So 3, that's how many we can confirm survived. Okay, now our reefs suffered a lot. Most of them died off. These hexacorals had to diversify, evolve, and adapt, and turn into the scleractinian corals we have today. But what caused this? The reefs themselves, the corals themselves, the animals in that coral did not die. From what we can tell, their symbiotic algae did. Nice scarf. How quickly he took that off, that was great. It's all right, scarves are great. You can wear a scarf. Okay, so coral have this symbiotic relationship with a certain type of algae. These algae live in the coral animal itself and digest any food that the coral eats. This way, the coral animal can just focus on catching food and utilizing the nutrition to grow itself. And the algae get to subsist off of whatever the coral eats and then digest and then give that energy back to the coral. Okay? Symbiotic relationship. Not parasitic, both parties get something out of it, okay? So what seems to have happened here is the symbiotic algae living within the hexacorals died off. And this caused, in turn, a die-off of hexacorals. The coral reef systems really suffered until a little bit into the Paleogene, and we see them start to come back. These new scleractinian type corals begin to show up, and we believe it's because they were able to form a new symbiotic relationship with a different kind of algae, one that was more evolved, more adaptable to the new environment. Okay? So what fills the niches left behind by our large predatory swimming reptiles, our plesiosaurs, our pliosaurs, mosasaurs, all of these things? The gigantic turtles the size of this room, right? What would have filled those niches? Mammals. Okay? It doesn't take that long at all before we start to see whales show up in the fossil record. Okay? As a matter of fact, whales and sharks become the super predators after the dinosaurs die off and after the swimming reptiles are gone. Okay? So the mammals that were alive during the time of the dinosaurs were generally small, kind of rodent-ish, okay? Kind of like big rats or capybaras, okay? We go from those type of animals and we start to see the development of the swimming, or of the swimming mammals that we have now. It doesn't take that long. This guy already is starting to swim. This guy is not fully aquatic, more like a beaver. This one's fully aquatic. Then we see our super predator whales show up. And then they evolve from there to the whales that we have today. There's really only a few species of whale in the ocean today that are still what we would consider predatory, okay? Most of the whales we have today are humpback whales, are blue whales. They are baleen whales. That means that they have big sifting nets in their mouth, basically, that they take a big mouthful of seawater and then squeeze the water out and then lick off all of the yummy little fish and krill and whatnot that's left inside their mouth. But sperm whales and orcas and dolphins, they actually have the teeth and the jaws for catching fish and eating stuff, and seals and penguins and all of that. Those are the descendants, the closer descendants of our predatory, super predator whales that we see during the Paleogene. Yeah, Jackson, you had a question?
That's what I was going to ask, like what the super predators are.
Oh yeah, there were some big ones. Okay, Basilosaurus was a 60-foot predatory whale. Ate great white sharks. Yeah. Okay. Now, speaking of great white sharks, you see the great white shark jaws in this picture? It's those ones. Yeah, this is a megalodon jaw. Carcharodon megalodon and Carcharodon carcharias and Carcharodon megalodon. Cousins in the same genus, very similar body size, not body size, but body shape. And the difference being, megalodons were 60 to 70 foot long sharks. And this is a megalodon tooth right here, real one. I have another one out in the display case, a bigger one out in the display case outside my office.
That was a small tooth?
This is a fairly small megalodon tooth, yeah. The one I have out there in the display case is almost twice as big as this. Okay. Teeth the size of my palm when they were fully grown. Yeah. Those were among the apex predators, okay, that filled in after the dinosaurs went away. Okay, so what's happening on land? Are plants spreading outward? Flowering plants have been around since the Cretaceous. But we don't really see the development of a lot of new groups with the exception of one. Grass showed up during the Cretaceous. There's evidence that grass started to appear during the time of the dinosaurs, but it didn't really become popular until the time of the mammals. Grass started to fill in spaces on pretty much every continent very quickly during the Paleogene. Now, grass is very interesting. Grass is an angiosperm, a flowering plant. There are many different types of grass that you may not even think of as grass. Did you guys know that bamboo is a grass? Did you know that rice is grass? You like eating rice? You eat grass, right? Well done. You're eating grass seeds. Okay, so grasses through the Paleogene continue to spread out and fill in all of these places, all these ecological niches across the planet, okay, on land. Now, here's our Cretaceous right here. This is the development of mammals. Notice that there were only a few groups of mammals, many of which died off fairly quickly, during the time of the dinosaurs. We had our monotremes, okay, so platypi and echidnas. Our marsupials, kangaroos, wombats, koalas, okay? And then the only placentals that were around at this point in time were multituberculates, which think of them as very large rodent-like animals. Okay? They were the most successful mammal group during the time of the dinosaurs up until the dinosaurs went extinct. Then they got really successful afterwards, but then what happened to them? They pinch out here. They die. Why do they die? Why do you suppose the multituberculates died? After their biggest predator, the dinosaurs, went extinct, what happened to them?
Because it was starting, they had more different predators.
The environment could have changed. What? Different predators? Sure. Absolutely possible. What else? Competition. Competition for food and living space. Look what's happening to the rest of the mammals. All of the living space and food supplies, which the multituberculates have been relying on, are now having to be shared with all these other groups. And what happens if any of those groups have evolutionary advantages? Multituberculates get the short end of the stick. And we see that's what's going to happen here in a minute. Okay. So, during the Paleogene, we end up with about 100 different families, which is approximately the same number of mammal families that we have on the planet today. Okay. Horses were about the size of house cats during this time. This is a horse. What it would have looked like during this time period. Huh?
How big was a cat?
How big is your cat? Do you have a cat? Have you ever seen a cat? Like that. Horses were about that big. Okay? Because remember, we're going from these small rodent-like animals and diversifying from there, right? Things are going to start small and get big to fill in those niches. Okay? So, only 12 million years after the end of the Cretaceous, do we already go from these rodent animals to bats and whales. Okay? Both groups, swimming whales and flying bats, swimming and flying mammals, all showed up only 12 million years after the dinosaurs went extinct. Life took very little time to diversify and fill all of these spaces. Yeah?
What do you mean by flying bats?
Bats that fly.
There were bats that
They all fly.
No, but what I'm saying is I also said swimming whales, right? And what I'm talking about here is I'm trying to illustrate how vastly different those two groups are from each other. They came from the same central ancestor. In only 12 million years, you went from this common ancestor to whales in the ocean and bats in the sky. That's very little time, evolutionarily speaking. Mammals are extremely adaptable. That's why we stuck around for so long. And why, after the dinosaurs went away, why we were able to fill in the planet like this. What gives us this extreme adaptability? Honestly, a big part of it is the fact that we are warm-blooded. We do not rely so much on our environment to give us what we need to get up in the morning, to go and get to work, to do what we have to do to survive. We don't have to wait for the sun, right? We just eat something and get going, okay? It's a very, very important evolutionary trait we've got. Okay, so our mammals, from this point, start to develop hooves. Okay, and so we're going to split our hoofed mammals into two different groups, even-toed and odd-toed. We call these ungulates. Okay, so our even-toed ungulates include camels, bison, and pigs. They have 2 or 4 toes. Okay, our odd-toed ungulates, horses, tapirs, rhinos, they have 1 or 3 toes. Okay, how many toes do horses have? 1. That one hoof, right? How about rhinos? You ever seen a rhino foot? 3. They have 3 toes, with each of which has its own hoof. Okay? Elephants show up during this time. Okay? Our first elephant ancestor looked something like this. This is Moeritherium. Do you see the elephant in that?
In the bottom one, yeah.
Okay, well, we'll get to Paleomastodon in a second. Moeritherium. Do you see the elephant in this? If you ignored the head and the feet, this would kind of look like an elephant body.
It looks like an obese rat. It looks like a really big
It came from those rat-like animals, right? Remember, they all came from this common source and diversified into the different ecosystems. So Moeritherium would have stood about this tall. Yeah. But yeah, you're right. It looks like it has a lot more in common with a rat. Look at those ears, very rat-like. Look at those teeth. Those look mean. Those weren't used for killing, though. Those were used for digging through the mud and looking for roots and stuff. Okay? These were herbivores.
So it had teeth coming out of the front instead of like...
Yeah. Yeah, and look at Paleomastodon here. Do you see how we go from here to here? Yeah. Do you see how we are starting to develop more elephantine characteristics? Look at this kind of little wiggly nose there. It's turned into a short trunk here. Look at these teeth have started to become tusks. This body has gotten bigger. Now it's standing almost up to the ceiling in height. Okay, we're looking more elephant-like here. Look at those ears, far more elephant-like, right? Okay, so elephants are progressing through the Paleogene. This is a multituberculate. Okay, that most successful group of mammals during the time of the dinosaurs. That's what they would look like, kind of a cross between a rat and a beaver, kind of capybara-ish, right? Now, multituberculates were successful until one specific group of competitive mammals showed up, and that would be the rodents. Rodents had several advantages over multituberculates. Yeah.
So in that top picture, did that come before the rat, or did the rat come before that?
This guy? No, this guy was around during the dinosaurs. This guy came in the Paleogene. Okay? So how did our most successful group of mammals die out? It's because the rodents showed up. Rodents fill the same niches. They need the same food. The difference being rodents had an adaptation of continuously growing teeth. You and I, how many sets of teeth do we grow?
Like 32.
We go 2 sets.
I didn't ask how many teeth we grow. How many sets of teeth do we grow? 2, right? We shed our baby teeth and grow in permanent teeth. Every now and then you'll have someone with a weird mutation to keep growing sets of teeth, but that's not the norm, okay? Rodents don't do that. Rodent teeth continuously keep growing. They are not the only animals that do that. Quite a few mammals do that, but these were the first ones. So what advantage did that give them over multituberculates? If you're multituberculate and you live for a few years and you spend all those years eating every day, chewing hard seeds and nuts and wood and such, your teeth eventually wear down and you die simply because you can't eat. But if you're a rodent and you keep growing your teeth over and over and over and over and over, each rodent on a one-for-one basis was able to live longer and healthier than the multituberculates were. And thus the multituberculates died off as the rodents became more popular and began to spread everywhere else. Okay? So that's how the multituberculates went the way of the dinosaur there. All right, this is the largest land animal ever, or land mammal, I should say, to ever exist. This is Paraceratherium. They stood about 25 feet long and 20 feet tall. That's about a 2-story building. Okay, we are on the 2nd story of this building. We would be able to reach out this window and pet the head of a Paraceratherium. Yeah, bigger than a giraffe. Do you know what the closest living relative to these guys is today?
Kangaroo.
Camel, giraffe, what? Kangaroo? Any other guesses?
Wait.
Looks like a horse? Anyone else?
Looks like a sheep.
Actually, the closest living relative to these guys, their descendants are rhinos. Yeah.
I thought that was stupid.
Look at the armored skin folds here along the joints, right? Look at the ears, the shape of the head. All it's missing is a horn, and that would look like a rhino head, right? So these guys, over time, their descendants became shorter, squatter, broader, and grew those horns, and those are rhinos, okay? But these were the largest land mammal ever to live that we know of, okay? The largest mammal predators at this point in time are these 2 groups, Mesonychids and Creodonts, okay? These are both the ancestors of cats and dogs. Cats and dogs come from these groups. At this point in time, cats and dogs are combined, okay? Think of this as a cat dog, and when you look at it, you can really see how it has both cat and dog characteristics in it. You want to pet it now? It would probably bite your arm off. Yeah. You would stand about this high next to that guy. Yeah.
That thing is, how tall is it?
Yep, 7 feet. Yeah, pretty big guys. Big predators, okay? But yeah, dogs and cats come from these guys later on. All right, now let's talk about birds. Oh boy. I don't know how long my microphone has been off, but I hope it's not that long. That could really be bad. If you missed out on any part of this this presentation, you can go to last term's 1404 and fill in the holes by watching what you missed here. You'll be able to follow along with where the slides are. Okay. I don't know where I lost audio, so I don't know where I can go back and fill in the spaces. Okay, so hopefully my microphone actually stays on this time. Okay, so Neanderthals in Northern Europe and Asia actually developed communities. They stuck together. They made houses and groups of houses. They seem to have had some form of empathy. They buried their dead with gifts. Burying your dead at all is a sign of respect for the dead that indicates love. Burying your dead with objects like flowers and food and carved objects? Why would you do that? Maybe possible evidence of religion? Interesting. In a species not human like you and me. How odd. Okay. So Neanderthals live up there for a while, doing their own thing. And then 150,000 years ago, actually sooner than or earlier than that, some people contest. So I'm going to say 150 to 200,000 years ago to encompass all of the people who believe it may have been earlier. Homo sapiens show up. They move out of Africa. They move up into Europe and over into Asia. And what do they find there? They find a group of bigger, slightly dumber people. And what do humans historically do with people that they perceive are lesser than them? Yeah, they like to take them over. So that's apparently what happened. Neanderthals disappear at the same time that Homo sapiens show up. Coincidence? I think not. So as Homo sapiens, us, are taking over all of these ecosystems, building our cities, developing our communities, Neanderthals go away. They go extinct. However, not entirely. I have a very small amount of Neanderthal DNA, as do all people who have ancestors that came from Northern Europe. What does this mean? There's only one way I could have Neanderthal DNA. Not all the Neanderthals were killed. Some of them got incorporated into Homo sapien culture. Now, that sounds really nice, but that could easily mean Homo sapien married a Neanderthal, or it could also mean Neanderthals were taken as slaves and raped and so on and so forth. Okay? So either way, Neanderthal DNA gets into our gene pool, and here it is. All right? Now, Homo sapiens had a big advantage. Slightly larger brains, sure, but they were smaller bodied than Neanderthals. They weren't as big, bulky, brawny, muscly. How did they win? Tools. As early as 150,000 years ago, they were making armor. We have art, paintings from them back 120,000 years. Carvings from them back 40,000 years. This is a flute that is tens of thousands of years old. It probably went even further back than that. We just don't have any relics that old yet. So, here we are. We've entered the scene. We've taken over the scene, actually. It's ours now. Belongs to our species. What's happening to the climate? Well, it's starting to cool off again. Okay? So, here in North and South America, we've formed this land bridge. Okay? The Panama Land Bridge, which allows species to move back and forth. Now, do most of them do that? No, but do some of them? Absolutely. And as they move back and forth, they begin to adapt to the different ecosystems. Colder up here, warmer down here. So we see some types of sloths up here and some types of sloths down here. Wolves up here, wolves down there, right? Turtles, turtles, so on and so forth. This sharing of species across this land bridge begins to occur, okay? Probably often as a result of the need for migration as things were cooling off. A lot of things moved down south, right? Okay, so here we are at, quote, the Ice Age, the Pleistocene Ice Age, okay? This is the size of the ice cap that covered the northern hemisphere during that last ice age. Went all the way down here, pretty much all of Canada and the top third of of America, the United States, covered in ice during that glacial maximum. Why did this glacial maximum occur in the first place? Well, it's going to come down to tectonics again, believe it or not. We get that positive feedback loop, but what causes the beginning of this positive feedback loop? In this case, it likely had something to do, at least in part, with that land bridge, Panama. Prior to the joining of North and South America, the Atlantic and the Pacific Oceans were able to share water with each other between these two continents. After Panama formed, none of that. The Atlantic Ocean became colder, became saltier. And so as cold water goes up north, instead of warm water, it doesn't melt any of that, and that ice sheet continues to grow and grow. That ice cap gets bigger and bigger and bigger as cold water feeds more and more into the system. As our ice sheet gets bigger, it reflects more solar energy, and we get the positive feedback cycle into a glacial maximum. Okay. It's also during this time, beginning about 850,000 years ago, that those Milankovitch cycles begin to dictate our warming and cooling trends. Remember those Milankovitch cycles? Where you have Earth elliptically orbiting the sun, spinning on an axis, and wobbling, doing this, right? Those are the Milankovitch cycles. So right about now, 850,000 years ago is where we believe that began to being the major contributing factor into our glacial maximums and global warming trends. All right, our forests are responding to the advancing ice sheet, okay, to the glacial maximum as it's growing. By the way, that was called the Wisconsin, okay, that glacial maximum, all right? So right now, during a glacial minimum, we see something like this, okay? This is kind of a cross-section view of Europe. Paris, Hamburg, Germany, all under deciduous forests. Stockholm, Sweden, we're starting to move into more of a boreal conifer forest. Moving up north, way, way up north, we start to see birch forest and then tundra. Back during the last glacial maximum, Paris would have been under tundra. Germany, Hamburg, Germany, and Stockholm, Sweden would have been under the ice sheet, okay? Just kind of a sideways view perspective on what we're looking at here. In North America, after the end of the Ice Age, we see massive lakes form. Why would there be all of these lakes in North America? Well, because all that ice melted. Where is that ice going to go? The water's got to go somewhere and makes these giant lakes. That's how we get the Great Lakes. There was another Great Lake called Lake Agassiz, over here, okay? Lake Lahontan over here, Lake Missoula, Lake Bonneville covered most of Utah. Lake Bonneville, all of these lakes are gone with the exception of the Great Lakes and the Salt Lake in Utah. The Great Salt Lake is what's left of Lake Bonneville. All right, tectonics still happening, okay? So the Basin and Range Province out here in, let me go over there and show you on the map, okay? The Basin and Range Province is a series of valleys and mountains out here, right there. This is the Basin and Range Province. This happened as North America was getting stretched, thinned here in the middle, tectonically. And so you get these fault systems. And so you get a fault block and a valley and a block and a valley and a block and a valley between all of these faults. And that's what makes our Basin and Range Province that formed here during this time. The Sierra Nevadas out here in California, they are uplifted plutons, usually Jurassic. But so that's how the Sierra Nevada mountain range formed during this time. Plutons that got pushed up from deep underground. Okay. The coastal range orogeny, this is the last orogeny that you're going to learn about. Okay. Cordilleran happened here on the west coast. This was the last big episode of volcanism that has happened out there on the west coast. Okay, so we get a lot of igneous rock piled up on top of itself, adding to the mountain ranges out there. And the San Andreas Fault formed during this time. As all of this ice was melting and it's rushing away, it's scouring out a whole lot of material on its way to the ocean. All of this melting ice since that last ice age has scoured a lot of material, leaving what we call scablands. Particularly out here in eastern Oregon and Washington, you'll see these, where a whole bunch of sediment has been stripped away by all of the meltwater from these glaciers. Something else that happens, the Himalayas begin their big push upwards. Everest stands about 5.5 miles high. It's pretty high up. That's pretty tall. Yeah. Drive 5.5 miles and then imagine that straight up. It's pretty intense. Okay. So, Australia and India are actually riding the same plate. So as India slams into Eurasia, it starts to slow down. You see 10, 10, 10, 10, 10, 10. But you can see the motion of India start to slow down as Eurasia starts to absorb that energy. Okay, Himalayas rise between them. You can actually see Australia doing the same thing, where it's moving, it's moving, it's moving, it's moving, and then all of a sudden it shifts direction. It starts off going this way and then takes a hard left. Why? Because the plate that it's riding on with India got stopped over here. If I'm moving my arm and then I stop it here, the rest of this arm is going to keep going, but it's going to change direction, right? That's exactly what happened here. Okay, Australia's motion was changed by the impact of India with Eurasia there. And then finally, the Alps start to rise. Why are the Alps rising? They're in Europe because Africa is continuing its own collision with the other side of Eurasia, while India is colliding with it on this side. So India hitting it on the east, Africa hitting it on the west. Both start to form mountain ranges. It's just that India hit first. Hence, we have the Alps, or the Himalayas, the Alps forming right now, still continuing to form, and there's going to be another much larger mountain range there, bless you, in a couple 10 million more years. Okay. Any questions about the Neogene? All right. Let's keep on trucking through the Holocene. If it decides to load anyway. All right, Holocene. All right, so the Holocene took place 11,700 years ago to now. We are still living in the Holocene. There is a large group of people who believe that we should rename it from the Holocene to the Anthropocene because humanity has been the largest biological change, biological influence on this time period since the last glacial maximum. It seems pretty hubristic to me to name a whole time period after ourselves, but I can see where their argument's coming from. Luckily, I don't have to make that choice. Okay, but what has happened during the Holocene? Mostly stuff that we've done is the most interesting, most influential stuff to talk about. Deforestation, the development of cities, industrialization, massive quantities of greenhouse gases spewed out, the development of transportation, right? Overhunting, extinction, This is what's been characterized during the Holocene. Okay, so the glaciers retreated. 12,000 years ago, they were right here. Now here we are, right? We are already living in a period of warming before we started the Industrial Revolution. It was already happening. Excuse me. The best way for us to see the historical rise and fall of modern sea level, because the layers of rock haven't been turned into rock, the layers of sediment haven't turned into rock yet, is to actually study the growth of coral reefs. Coral reefs will follow the sun. And so if you're seeing this coral reef start to grow up at this certain angle, you can adequately determine it's following the shallow water to keep up in the sunlight. And if it's going towards land, that's sea level rise. If it's going away from land, that's sea level fall. Okay? So we can study more recent ocean level rise and fall that way. North America was first settled by a group of people who crossed a land bridge between Russia and Africa about 13,000 years ago. So this is during that last glacial maximum, which is why there was a land bridge. Sea levels were small enough, low enough, that this area of ocean bed was actually exposed. And so people were able to cross from here to there and into North America. Then the glacial period ended, sea levels rose. That is now under about 800 feet of water, give or take. But it's still there. That land bridge is still there. It's just covered in water right now. The first actual civilization in North America we can confirm was called the Clovis civilization. Right now, all we have left of them are really their spear points, arrowheads, and such. It's believed that they were wiped out when a comet landed in North America not far from their center of civilization. And the survivors would have spread out from there to form the later groups that came after them. The Holocene also is characterized by the extinction of pretty much every large mammal on North America. Woolly mammoths, woolly bison, North American camels, all of them. Why do you suppose this happened?
Because temperatures rise stuff.
Sure, environmental impact, absolutely. What else? Anything else you can think of that was happening about 13,000 years before?
Our human activity got rid of a lot of animals' habitats.
Yeah, we showed up. So 13,000 years ago, that corresponds to the arrival of humanity on the scene. So temperatures worldwide were starting to rise, which means that all of our animals that have adapted to cold weather were needing to adapt to warm weather, and most of them probably would have. There would have been, absolutely, there was a die-off. Right? There was a die-off every time that there's an extreme weather change. An ice age shows up or an ice age ends, there's always a small die-off. But if I have a herd of woolly mammoths, actually let's not say herd, let's say I have 20,000 woolly mammoths across North America, okay? And over that climate shift, without humanity being involved, 18,000 of them would have died off, but the other 2,000 would have adapted quickly enough to survive. That would have been fine. They continue, their civilization, or not civilization, their population comes back eventually. You add humanity into the scene, while the environment is shifting, while all of these animals are under environmental stress to adapt, humanity also shows up and starts eating them. So 2,000 survivors really quickly becomes none, right? If you follow my example there. So the combination of environmental change plus human involvement led to this mass die-off of the largest species in North America. Agriculture starts to show up, okay? Right here, 8,500 BC in Greece is where we first start seeing people have herd animals in large quantities, start to actually grow plants for the purpose of having a crop. It spreads out from there, makes it to France, 5,400 BC, the British Isles, 4,000 BC. By 6,000 years ago, it's everywhere, agriculture, okay? Specifically, purposefully growing crops for sustaining a population. Usually wheat and barley, those were the two most common ones to start off with. Okay. The oldest life form that we know of on our planet is a tree. I should say large life form. I won't get into that. But the oldest confirmed one that we have is 4,600 years ago, or old. It is this tree. They call it Methuselah. It is a white pine. In Nevada, I want to say, is where it lives. But it's still alive, and it's been around for 4,500 years. Trees have the ability to stay alive very, very long if they live in the right conditions, where they are not targeted by insects and climate change doesn't affect them too much. Okay? We study tree rings to learn a lot about the environment in more recent history. We can see what the ratio of gases in the atmosphere was. We can see what the rainfall was like over those years by studying tree rings. Over the last couple of thousand years, especially over the last several hundred years, humanity has quite affected our environment, in particular the atmospheric chemistry. This is how much carbon dioxide has been put in the atmosphere over the last couple hundred years. What happened right there? The Industrial Revolution, the discovery and widespread use of using coal. Coal had been used before then, for sure. But the widespread use of coal for industrial purposes started here in Europe and only got bigger. We've put a lot of carbon dioxide in our atmosphere. We have increased the temperature of our planet by 1.3 degrees Celsius over the last 100 years. And we have an estimated 4 to 9 degrees Celsius increase to go by 2100 over the next 100 years. That's estimated, and that's a very large range because that's not taking into account what may happen between now and then to pump even more greenhouse gases in the atmosphere. Now, this doesn't just affect the atmosphere. This also affects the ocean, because there is a flux, a balance that is held in the chemistry of our atmosphere versus the chemistry of the ocean. Gases in our atmosphere are shared with the ocean and vice versa, which means that as the atmospheric concentration of CO2 increases, so does the concentration of CO2 dissolved in our ocean, making it more and more acidic, carbonic acid acidic, which is going to do what to the shells of everything that uses calcite? Dissolve it, make it brittle, make it thinner. And this is what's leading to the mass die-off of things in the oceans that we are seeing now. As ocean acidification increases, so does the amount of things that die off in the ocean. It's only going to get worse. And then, of course, there's the ice caps are melting. We're all going to die. Thank you, Al Gore, for that timeless classic comment. All these blue spaces are places that have already melted in the last few decades. Everywhere that's white, that's going to follow in the next few. We're going to see a lot of sea level rise. Sea level is already rising at an increasing rate. Presumably, by the year 2100, oceans will have risen by about 100 feet. Not 100 feet, 10 feet. Huh? Covered again? Oh, Texas? No. I mean, parts of Texas will. Have you ever been to Corpus Christi? It's going to be underwater. That whole part of Texas is going to be underwater. Anything that's... Huh? You want to go scuba diving? Go scuba dive through the city. It'll be underwater. Yeah. All right. That's it, my friends. Next time we meet is the final exam review. Any questions for me? Okay, I'm going to end this recording here then. Don't forget, my online students, to send exam review questions before our next meeting.